Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Wladimir Lyra with us today. Hey, Vlad.
Thank you. Happy to be here.
Well, thank you for agreeing to talk about your very lovely article. And Vlad, where are you located at?
I'm in Las Cruces, New Mexico.
Radio telescope land.
Yeah, that's up the I-25. Yeah, we are actually here. Yeah, we are a little south from there.
Yes.
Going up there to the VLA is kind of a 3-hour drive. A beautiful one.
It's a beautiful one, and it's fun to be out there. And on occasion, you get to walk on the dishes out there, so it's very cool. Very cool. That's a nice telescope you have over here. You have two of them. You have a little spotter, and it looks like you got a sun spotter there. Yeah, very cool.
That's true. Yeah, that's a telescope that I got from the Astronomers Without Border.
Yeah. Okay, very cool. So you use that.
Fortunately, sorry.
So you use that in your class or courses or something?
I once gave an exercise in a course, in an intro course for the students to put an azimuth wheel on it so that you can point. Because funnily enough, the first time that I tried to use it without a pointer, I couldn't even point the moon. So that was embarrassing.
Very cool. Very cool. And Wladimir, what do you like to do for research?
So yeah, I work on computational astrophysics, and that's the methods, right? I use, but I'm mostly interested in the theory of planet formation. That is how planets form, right? The origin of the Earth, the planets on the solar system, exoplanets, and essentially the processes that take place while planets are forming.
Cool. Very nice. And that is going to bring us to this very awesome APJ article. It is the open access era, people, and this article is open access, so you can go get a copy for free. Go grab one. An analytical theory for the growth from planetesimals to planets by Polydisperse, Pebble, Accretion. And Wlad, take us away.
Thank you. Yeah, first I would like to acknowledge my co-authors here. That's an article that I would not have been able to do alone, right? So Anders Johansen, that's the second author that you see there, from the University of Copenhagen and in Lund in Sweden. Sweden also is where I did my PhD, actually. I did it
I didn't know that. Cool.
Yeah, not in Lund, but in Uppsala.
Okay.
Manuel Canhas is a graduate student here at our department. He started in 2019 and just finished with a master's. So that is that paper is actually an offshoot from the work that he did. I'm going to go back to it. Okay. And Xiaoqin Yang, he was at the University of Las Vegas and recently moved to the University of
Tuscaloosa.
Alabama. Yes, exactly. That's Tuscaloosa. So yeah, thanks a lot for asking me to present the work here. So this is this is an interesting update on the theory of a Pebble accretion. That it's a theory that we started working on some time ago, since around the time that I was actually doing my my PhD. I would say that and that's something that I do say here, right, in the article, in the introduction. So this theory, the theory of a Pebble accretion contrasts with the theory of planetesimal accretion, right? For a long time, since the 90s or earlier, it was thought that the main way that you build planets is that you form first the planetesimals, and then these planetesimals collide with each other to build bigger cores, right? And then in this way, you can go and pass right from kilometer-sized objects, these are the planetesimals, to bigger cores that can collect more of these planetesimals that keep growing, right?
I'm with you.
Through gravity. Yeah, that's called the planetesimal hypothesis. So the work that was done in the 90s, there is this famous article by James Pollack, was a student of Carl Sagan. He came up with this theory of planetesimal accretion, right? I mean, he worked out mathematically, numerically, how to build the bigger cores, right? Through building them just by accreting planetesimals, right? Until they get to the size of the cores of the giant planets. And that is great for Jupiter, right? But already when you try to apply that to Uranus or Neptune at the location where they end up taking too long to form these cores, right? Actually, if you try to form a Neptune in this way, it's going to take longer than a Hubble time.
Okay, so that doesn't work.
So there is something off there, right? And back in the 2000s, you were seeing that in fact, if you have gas in the system, which is the environment where planets are born, you can significantly accelerate the planetesimal growth, not by having the planetesimals collide with other planetesimals, but by having the first planetesimals that form accrete the little rocks that are suffering gas drag. So the gas drag makes the motion dissipative. And once the motion is dissipative, it's very easy to lose energy and then accrete. That is a main problem with the planetesimal accretion, is because they need to lose energy. I mean, they can't, right? If you are in an environment that is not this dissipative, the cross section ends up being too small. So the drag force ends up maximizing the cross section, and therefore Pebble accretion accelerates planetary growth by orders of magnitude. So as I say here in the paper, the first time that this was seen was in a paper that I mentioned here, like my paper from 2008, but I did not recognize what it was, you know. So we saw that
hindsight.
The first planets that form, they were growing very, very, very fast. Like in a few orbits, they would double in mass. But then Anders, the second author of this article, he saw very fast accretion rates onto planetesimals, and then for the first time he suggested that a significant fraction of planetary growth actually is done through this phase of accretion of pebbles and rocks, not through planetesimal accretion, right? And then after that, he hired a graduate student, Michiel Lamberts, who is the paper that is quoted down there. Lamberts and Johansen, 2012. And Michiel did an excellent PhD thesis developing that. And that now has grown to be the paradigm, right, of how planets form.
Paradigm shift.
However, there is one problem in there, is that Pebble accretion seems to work only when the seed planetesimal that is accreting the pebbles is already very, very big. So you still need to go through a phase. So you still need to grow through a phase of significant growth through planetesimal collisions once those when these planetesimals are still small. So that ends up still being a significant bottleneck that you still need a phase of significant growth to double, triple the mass only through planetesimal collisions until you actually get to the mass where you can start having Pebble accretion.
Right.
So the need for this phase of planetesimal collisions was until this article a problem in the model. So in this paper here, we solve it, right? We find out that actually there is a way to bypass that, and you can have a Pebble accretion directly on the first planetesimals that form.
Okay.
Right?
All right.
I would say that this is the last nail in the coffin of planetesimal accretion.
Yeah.
So how is it that we achieve that?
Yes.
What we see is that you're gonna find orders of magnitude higher accretion rates than the usual Pebble accretion, if you consider that the protoplanetary disk has a distribution of Pebble sizes. So the planetesimals are not accreting a single Pebble size. It is accreting from a distribution, right? I mean, because when you start, you have a disk that has only interstellar dust grains, but as soon as they get into the denser environments of the disk, they keep growing, right? So they grow through coagulation. Yes. And then if you start from submicron grains, you end up building bigger things, right? So these coagulation models, they find that you can grow up to millimeter size, centimeter size, right? So these are the pebbles that you have to start with. And then originally, the theory of Pebble accretion was developed with one single Pebble size, because the distribution is top heavy, right? You can have a distribution of pebbles, but most of the mass is on the bigger sizes, right? So yeah, that makes sense to use those. But what we find is that if you consider the smaller pebbles, you can end up having a bigger mass accretion rate there. So that is what I'm showing here in on the right side of figure 3. If you could show that, please.
Figure 3, the right side of figure 3. Let's slide down and right side of figure 3. Okay.
Right. So what we're seeing here on this figure 3 are the accretion rates that you get from what I call the monodisperse. Like monodisperse means only one size, right? One Pebble size. So that's the accretion rate. That's the thin gray line.
Yeah,
that's the accretion rate that you get if you consider only one, like one size, right? The biggest Pebble that is present in this model, which in this case we consider a Pebble size of 10 centimeters, right? And as you see here, like this accretion rate, it's quite close actually to the one that we get with this model now, that is considering other Pebble sizes too. They are more or less the same as you go to the larger sizes of planetesimals, right? There are accreting them. So sorry, I didn't describe the axis here. So the axis here on the x-axis, on the horizontal axis, you're seeing the mass of the protoplanet that is doing the accretion, right? So going from like 10 to the -6 Earth masses to about 10 Earth masses. So like, yeah, from very small to
large,
very big. Yeah. So for people that don't like look at these plots every day, that don't deal with these masses, 10 to the -1 Earth mass is about the mass of Mars. 10 to the -2 is about the mass of the Moon, right?
Good.
And yeah, and 10 to the -4, I may be saying something wrong here, but it's about the mass of Pluto, right?
Yeah.
And 100-kilometer size planetesimals is between 10 to the -6 and 10 to the -5.
Yes.
Right.
Okay.
And then the mass accretion rates that you get are on the y-axis in Earth masses per year.
Yes.
So the disk lives for about 10 million years, right? So it's here, if you have then a mass accretion rate of 10 to the minus 6,
yes,
then you are accreting a mass of material in 1 million years. If you have 10 to the minus 7, you accrete 1 Earth mass in 10 million years.
Yes.
Right. So the thick black line here is the accretion rates that one gets from this model that I show here in this article. So what are we seeing here? We're seeing that at the larger planetary masses, you have that the thin gray line and the thick black line are more or less the same, right? To within a factor 2-ish or so. But you see orders of magnitude difference as you go to the lower planetary masses.
Indeed.
Right. You see here the biggest difference between the thick black line and the thin gray line. So from the monodisperse to this model, if you consider more pebbles, ends up being 2 orders of magnitude, right? So 10 to the minus 4 is, as I said, the Pluto mass, right? And as you go to lower masses, then you start having even then you start to have significant accretion rate even on top of the small things, like the 100-kilometer objects that are the first planetesimals. And the other lines that you see here on this plot, so the blue line, the red line, and the yellow line are just different regimes where the planetesimals are accrete, or the protoplanets accrete the pebbles, right? So loose coupling is essentially the geometrical accretion. That's when the protoplanet is only offering its geometrical cross-section to accretion, right? The bondy is when you are in a regime that the protoplanet is accreting the pebbles within its bondy sphere.
Yes.
And then once it grows in mass, it's accreting now in what we call the Hill regime, because it is accreting the pebbles, all of the pebbles in its Hill sphere. The Hill sphere is the gravitational influence of the protoplanet. So in the theory of pebble accretion, you pass from this geometrical, the loose coupling regime, to the bondy, and then to the Hill, right? What this plot shows is that the biggest difference is in the bondy regime, right? The bondy regime is the red line, right? So so it's in this regime here that you see most of the difference, right? So that is the major finding, that the bondy regime has 1 or up to 2 orders of magnitude higher accretion rates in the polydisperse, like polydisperse meaning more than 1 pebble size, to compared, right, to the monodisperse rates. And also you see here that the onset of pebble accretion, of bondy accretion, is extended to 2 orders of magnitude lower in mass too. As you see here, if you follow the gray line onto the low masses, you see that the thin gray line meets the loose coupling at about 10 to the minus 4 Earth masses, right? But the thicker line actually continues on bondy regime up to lower masses. Between 6 and 5, right? So it's this area here where you have much higher accretion rates for bondy that we focus on here, right? So and why does this happen? So if you go to the figure just below it, the right hand side of figure 4, then we're showing here what is the reason for this to occur. That figure there. Thank you. So this figure also packs some, packs a lot of information in there. What you're seeing here is on the right, on the horizontal axis, we are seeing the size of the pebbles, right? The size of the pebbles that are being accreted, right? So going from 10 to the minus 3 millimeter, right, to 10 to the 2 millimeters, so 10 centimeters, so that's the bigger one. Then on the y-axis is the mass of the protoplanet that is doing the accretion.
The x-axis in the previous
pebble size. So the pebble size on the horizontal axis, the size of the protoplanet that is doing the accretion, and color-coded is the mass accretion rate, normalized by the accretion rate of the biggest pebbles.
Okay.
So as you see
Yep.
here, 1 would be the 0, right? Because this is in logarithm.
Long.
So the rightmost column is all at 1, right? Because that's the biggest pebble present in the model. So this plot here is showing that at the Bondi accretion rate, this is showing that the highest accretion rate for Bondi, for the Bondi accretion, is not the biggest pebble size that is present, right?
Okay.
So what you're seeing here is the polydisperse accretion rate that is being normalized by the monodisperse. So whenever these numbers are bigger than 1 in log here, so bigger than 0, that means that you have a higher accretion rate for a lower pebble size than the biggest pebble present in the calculation. That's the bright red here, right? There is this area here where you have the brighter, the bright red contours. In these areas, you have a higher accretion rate for a smaller pebble size than the biggest pebble size. And as you see, that happens only in the Bondi accretion regime. If you look at the figure just to the left of it, the figure 4a, is showing there the different regimes of accretion.
Thank you.
So the heel, the Bondi and the coupling geometric.
They are the same. Okay, got it. I'm with you.
Right. Okay. So what is going on there? In the monodisperse, you would be predicting that they are still in the geometric regime, but in the polydisperse, they are already in the Bondi regime. And the Bondi accretion it is much, much bigger. That's what is happening here. Right?
There, right.
Yeah.
Yes.
And, right. So why is that? Because the bigger pebbles, they end up in the Bondi regime. They sort of already behave like planetesimals, because the Bondi sphere, when you are in a low planetesimal mass, is very small, right? So the Bondi regime, what you are doing is that you are accreting a pebble. The best accreted pebble is the pebble that couples to the gas within the Bondi time. The Bondi time is the time that the pebble takes to cross the Bondi radius. If you are a big rock, right? If you are considering a pebble that is too big, right?
Okay.
What's going to happen is that this pebble is coupling to the gas on a longer time scale than the time scale that it takes to cross the Bondi radius. Therefore, it behaves just like a planetesimal would. So it's not, it's a bigger pebble, right? That is essentially in the planetesimal accretion regime. So that is not going to accrete as well as a loose, as a smaller pebble that is marginally coupled and therefore is suffering more drag, right? It's coupling to the gas at the same time that it takes to go through the Bondi radius of the protoplanet.
Cool.
Yeah, so that's why this is happening here. And what is the consequence of that? You have a bigger accretion rate, right, for a smaller pebble size. Right, and you have those pebbles in your distribution. So if you go then to the right-hand side of figure 6, figure 6b, we're measuring there.
Figure 5.
Yeah, we're measuring there the accretion timescales.
Okay.
Right. There we go. Yes, the figure 6b there.
Did I get that right?
So what is it that we're showing in here? Again, let me go for the axis. What you're seeing here on the horizontal axis is the distance, right, to the star. So from 1 AU to 100 AU. On the vertical axis is the mass of the protoplanet that is doing the accretion, right? And color-coded here is the accretion time scale. So it's the mass divided by the mass accretion rate.
Yes.
As I said before, the disk lives for about 10 million years, right? So you have enough time to do significant growth, right? To double, triple in mass, if your growth time, if this accretion time scale is of the order of 1 million years, right? Anything that has a time scale Accretion time scale longer than about 1 million years, 10 million, is not going to grow significantly, right, within the lifetime of the protoplanetary disk.
Right.
But if the accretion time scale is less than that, then you can have a significant phase of growth just through this polydisperse accretion.
Cool.
Right.
Very nice.
Yeah.
Very nice.
So what do we see here? What are the planetesimals that have accretion times lower than 1 million years? So you follow the contour line of 6. That's the contour line of 1 million year.
Yes,
right?
That's the white line.
And you see that and this line starts to meet the black dashed line, right, at about 10 AU, right? So this line here, so this line here, this black dashed line, is the typical planetesimal mass. Is the planetesimal that is formed, is the typical mass of a planetesimal that is formed by the streaming instability, which is one of the favored mechanisms nowadays to form planetesimals. So the streaming instability is going to make planetesimals typically of the mass given by this black dashed line. And the most massive planetesimal that is formed by the streaming instability is usually 10 times bigger than that. So that would be the gray dashed line. Right?
We get the intersection right there.
So when this contour line of 6 meets these lines, right, these dashed lines, that's when you can have million-year accretion timescales on top of the bodies that are formed by streaming instability. So what is the conclusion that we get from this plot? The typical mass, the typical planetesimals have million-year timescales up to 10 AU if they're formed within 10 AU. You can push it up to like 20 AU if you say that the accretion timescale is the 6.5, so 3 million years, right? And if you use the gray line, so the most massive planetesimal formed, then you can push the million-year timescale up to even 40. Right? But actually, that's when you start growing into a bad territory, because you don't want things at 45 AU, 50 AU to grow too large, because we know on the solar system that we have the called classical Kuiper belt objects that are planetesimals, essentially. They are primordial planetesimals that remain the planetesimals, right, throughout the lifetime of the solar system. So those objects, they formed there at 45 AU and never underwent significant growth, right? So Pebble accretion shouldn't work for those objects. And that's what we see here too, right? The typical planetesimal masses that form, right, if they form at 40 AU, they do not grow, because their time scales for growth hit the contour line of 8, as you see here, between 7 and 8, right? So they take much longer than the lifetime of the disk to grow. That was a concern that I was having, like, oh, we find now that that polydisperse Pebble accretion can form protoplanets on top of the seeds, right, of the small planetesimals. But if that works in the Kuiper belt, if that would work in the Kuiper belt, that's bad news, because you don't want that, right? You want that to work in the inner disk, but not out. And this is exactly what we see here. We find million-year timescales on top of the planetesimals up to about 20 AU, but not beyond it. So that's pretty good. All right.
Very nice.
So the conclusion is this: that a phase of significant growth by planetesimal collisions, which is a problematic feature of the traditional core accretion model, is avoided.
Very good.
And not only that, this conclusion is supported by the lack of craters generated by kilometer-sized objects on Pluto. There is no, you don't find craters, right, generated by kilometer sizes on Pluto. What does that mean? That Pluto probably did not grow by planetesimal accretion. Probably grew by Pebble.
Right. Small ones.
Yeah.
Right. Less mass.
And and then a shout out also then to the New Horizon community for doing the exploration of Pluto. Alan Stern, Casey Lizzie, Orkano Ummerhan.
Good shout outs.
Thanks.
Good shout outs.
That's awesome.
Very cool.
The flyby of Pluto and Arakoth.
Oh, I'll come back.
And there's a few cherries on top here that I'd like to highlight. So if you go to figure 2.
Figure 2. I like cherries.
Yeah, if you go to figure 2.
Figure 1, figure 2. There we go. Whoops. Where'd figure 2 go on me? There it is. Sorry.
Right.
My bad. Okay. Here we go.
So as you see, this article has 83 equations in it. Right?
Yes, it does.
So
it's a record. It's a record for these videos. 83 equations. Very good.
Oh, really?
Yeah.
Yeah, because this is a paper that combines analytical theory with numerical calculations. So what we are building here is analytical theory, right? And we found here in this in this work, that's what I'm showing in this this figure, is an exact solution for the monodisperse Pebble accretion rate.
Okay.
So as I said, right, the theory of a Pebble accretion was first made for monodisperse distribution, and if you see the articles by Lambertsen and Johansen back in 2012, that came up with the theory, they make the distinction between 3D and 2D accretion because these are limits, right, that they're physically relevant and it's simpler also to solve analytically. What this figure here is showing is that we could, in this paper, solve for the exact mass accretion rate without making the assumption of these limits, the 3D limit and the 2D limit.
Okay.
So the mass accretion rate, if you make the assumption of 3D, then you are accreting over the whole volume of the heliosphere, right? Of the accretion radius, and you can assume that the density of pebbles that are being accreted there is constant, right? So you have a constant density of pebbles, and the protoplanet is accreting from its whole accretion radius. So you have the volume of the sphere there. Now you can also do the opposite accretion. You can do the opposite limit to the 2D limit. So then in the 2D limit, what is going on is that the Pebble column is thin, is very, very thin, thinner than it's so thin that essentially the protoplanet is accreting a line, right? I mean, going through the distribution of pebbles and accreting. I mean, it has a cross section that is much bigger, right, than the thickness of the pebble column, right? So that is the 2D accretion. So in the 3D accretion, you have the protoplanet going through the collection of pebbles and then offering all of its cross section, right, for the accretion. Now the physical, the complete picture would actually be if you have the stratification of the column of pebbles being of the same order of magnitude as the accretion radius of the protoplanet, right? So the density is changing within the cross section of the protoplanet. So that's what we did here. There was an article, Johansen et al. 15, that approximated that. So that's the other lines that I show here. So that's the square approximation, essentially like doing the the accretion not in the circle, right? That is the cross section of the protoplanet, but approximating it as a cube, right? I mean, as a square that is simpler to solve, and then multiplying it by the factor, the area factor, right, between the circle and the square.
Right.
But we could solve here the integral exactly. So if you just move to the side, if you show equation 31 and 32, that is the integral that one needs to solve for the complete mass accretion rate. That's the equation 31. So that if you solve that, then you can find what the exact mass accretion rate is. So the square approximation, right, as I was saying, was doing it's getting almost the exact one, but with that approximation. So what you could do here is to solve that integral there, the equation 32, right? So the total mass accretion rate is given by the equation 33, right? Essentially, the difference between equation 31 and 33 is that we defined this function S there, which is here the stratification integral, right? So I mean, it looks like a problem that you would do in basic calculus, right? Find find what this integral is. Well, it turned out that it needs a special function. So the solution for that is equation 34. And then the mass accretion rate, if you plug in there, then you find on equation 35, that's the total mass accretion rate. So this I0 and this I1, they are Bessel functions of the first kind.
Right.
So you wouldn't put that in a basic calculus course.
Limits of the Bessels. Okay, very cool. Very cool.
And then what is shown there in figure 2 is that this exact solution.
Right, that's the blue.
That's the solution. Yeah, it goes smoothly from the 3D accretion rate, which is the orange line,
up to the 2D.
So the exact one is the blue line, right? The 3D accretion rate is the orange, and the green one is the 2D. So it goes. You can follow the blue line, and then it passes smoothly from the 3D accretion rate for the smallest objects,
right,
to the 2D accretion rate for the biggest objects. So
very nice.
If you see some articles in the field, they usually always have this kink because they use the 2D
or the 3D
for the bigger objects, and then the 3D for the small objects, and just switch from the 3D to the 2D discontinuously once they pass the transition mass. It's a kink there, in the plot, because it has. And then in your codes, then you always would need to do if. If the mass is bigger than the transition mass, use the 2D.
Just do the integral. Do the integral.
Right. So it's much better to use something that is exact. So that's not the main point. So I call it one of the cherries.
Right. I like cherries. Cherries are good.
Yeah.
I like Bing cherries. I like Royal Anne cherries. I like all kinds of cherries.
Right. And the other thing is that I could find an analytical solution for all of these mass accretion rates here that we find in this article. So if you want to use this this model, you don't need to integrate numerically like I did here on this work. So when we first found the equations to solve, I looked at them and said, all right, okay. So now I needed to integrate them numerically to find the accretion rates.
Right.
And then Anders, the second author, said, well, maybe we could try to find the analytical solutions also for the mass accretion rates for the equations you find.
Okay.
And that's what we did. So we could find the exact analytical solution.
Very nice.
For the polydisperse to the Hill accretion, and a very good approximate solution for the 3D Bondi accretion. So that's what I'm showing on figure. What is the figure here? Let me. A second. So figure 11. You show figure 11.
I will get there. 1 sec. I will zoom down. Figure 11. Figure 11. There we go. Cherry number 2.
Cherry number 2, exactly. So this is the analytical solution for the polydisperse 2D Hill accretion, which is the appropriate, because the 2D accretion, as I said, is when the scale height of the pebbles is much smaller than the accretion radius of the protoplanet.
Okay.
So it can either be for very big pebbles that are sedimenting to the midplane of the disk, or even for pebbles that are not too sedimented, for bigger protoplanets, right? So that their accretion rate and their accretion radius is much bigger than the pebble scale height. So that will happen when the protoplanet is big, so you are in the Hill regime. And then the 3D would be in bond. The 3D is when either the pebbles are so small that they are lofted everywhere in the disk, or the protoplanet itself is so small that it is embedded in the pebble distribution. In that case, yeah, you are in the low mass regime, so the appropriate regime for that is the Bondi regime.
Right.
That's what you see. So having a 2D Hill analytical and a 3D Bondi analytical is exactly what you need for your model, right? If what you want is to predict like how big these protoplanets will grow. So that's what I'm seeing here. If I solve it numerically, that's what is called here the actual. That's the thick black line, right? And so that's the actual one. That's the one that is not making approximations, is solving for the full accretion rate.
Yep.
If I consider only in the numerical the Hill accretion, then you have the dark blue line.
Yep.
Right. The analytical solution that we find is the cyan line, right? The light blue line. As you see, it meets the actual and the Hill numerical right in the regime where you want that to be the case for the higher masses, for the higher protoplanetary masses. Right, the x-axis here, the horizontal axis, is the mass of the protoplanet during the accretion.
Yes.
So you have that being the correct mass accretion rate for the high mass protoplanet regime. And then the Bondi accretion is the numerical one. It's the red line.
Yes.
Right? Yeah. So that's the one that you'd get if you only consider the Bondi. Right. That's not the full case. You know that eventually for the high mass going to pass to the Hill.
Yes.
And then the magenta line, the pink one, is the analytical solution that we find in the case. And as you see, the magenta and the red meet at the lower masses, right at the transition mass. Right. So we have a correct analytical accretion rate in the low mass, the Bondi, the 3D Bondi, and a correct analytical for the high mass, the 2D Hill. I'm going to show how these equations are looking like, because that was fun also to show. If you go to equation 58 on page 10, that's the 2D Hill, right? That's beautifully simple, right? You have that's equation 58 there. So that is the integral that we need to solve for the analytical solution. ST here means it's the Stokes number. It's just a non-dimensionalization of the friction time. It's essentially measuring how important the drag is. Right. M is the mass of the pebble, A is the radius of the pebble, and W here is the distribution of pebble sizes, right? And then we solve it analytically. Yeah. So I defined this quantity double earlier in the article. But then, what is seen here is that if we make the assumption that this quantity W here is following power law, then you can solve this analytically and find equation 16. And that's the one that I plotted there. So that is the analytical solution for the 2D. As I said, right, just solve it. That integrates a power law, right? Yeah. We can integrate power law. That's something that you can give to a basic calculus course, and that's fine. And then you have the beautifully complicated one. Okay. That is the Bondi. So that one is shown, that integral is shown on, let's see, equation. Yes. So how do you solve the Bondi accretion? The Bondi accretion is equation 63.
Okay, want to start at 63. Yes.
Yeah. So that one was a tough nut to crack, but also turned out to yield something very nice in the end. So
Cool.
that is the mass accretion rate for the 3D Bondi regime,
Okay.
right? You have there, so the term that you see there on the first line is just constants, right? You have the Bondi radius, delta V, omega, that's the Keplerian flow. And then you have this integral here, right? And so in the 3D case, this F quantity here is just the 3D version of that W quantity. It's also a power law, but it has a square root in there. And yeah, so that makes it more complicated to integrate. And this function phi here is a shorthand notation for this equation 64. Don't worry about that. So because there is no analytical solution for this, that's when you had to do the approximation. If you go to equation 65, right? So splitting that integral into two integrals. Now, one thing that you notice is that because this function f, so the function f, I'm showing that without actually saying what these distributions are. So let me show this this distribution f, which essentially was like one of the it's the distribution function of pebbles. That is equation 11.
Okay, let's
go back to page 3.
Let's go to 11 momentarily, and 11, f of a. There we go.
Right.
Yeah, went to constants there. Dot central.
Right. So you see that square root there, right? So yeah, you have there. What is it that?
Okay.
Yeah. What is it that is showing there? You have. So sigma is the distribution of dust. I mean, the column density of dust. By the way, this is something that I do in my articles. If you scroll up, you're gonna see a table of all of the symbols.
Beautiful.
That's a table of all of the symbols used in this work. That's something I like to do in my articles because I find it frustrating sometimes when I'm reading an article and then I say, what does this quantity mean? And then you have to try to find it in the paper the first time you use it.
Right.
The hunt, exactly, for symbols, right? And sometimes they don't even.
Sometimes they miss it. So yeah, I totally endorse tables like this on theoretical work, right? Define your symbols, please.
So it's good to go there and see what these quantities are.
Yeah.
F distribution is the distribution of sizes of pebbles in the calculation. So yeah, there is that square root there. I'm gonna go back to it, but visually, that's what is plotted on figure 1 is the distribution functions.
Figure 1, let's go figure 1 momentarily. Yes, sure. Yeah.
Right. So there you see there on the y-axis is plotting the f function, right? So the f function is the grain distribution function in the midplane. So if you integrate this over the pebble sizes, this function would yield the number density of pebbles in the midplane, right?
Yes.
If you multiply it by the mass, then you have the mass density. So that's what is shown on the right-hand side there. So the mass density of pebbles, right? So you see here, this is the distribution. Now, because it depends on the square root, that square root is measuring the degree of sedimentation, right, of the pebbles. That's why on this left-hand figure, I am splitting between pebbles that are sedimented and pebbles that are not. Sedimented pebbles means that they overcome the drag force and sedimented to the plane of the disk, right? The unsedimented are the pebbles that are everywhere, right, in the disk throughout the whole atmosphere.
Yeah.
So that's where that square root comes in. And you know, I'm talking about the square root so much because it makes it impossible to integrate. There is no analytical solution for this. So if you go back to equation 65.
Yes. Yep, I'm with you.
Yep.
I'm with you. Let's go back to 65, and there we go.
Yeah, that was a trick that I only two unders, equation 66. You know, it was like square root of 1 plus x is approximately 1 plus square root of x. I was like, nah, that's BS. That's not going to work. But it does actually.
It does.
Because,
I mean, in those limits.
Yeah, it does. Yeah.
Okay.
Yeah, it is funny because if you go to the LaTeX file on the archive, I label that equation 66 equation funky approximation. Funky approximation.
Very good. That is a little funky.
Yeah.
What's the
right? In equation 67, I label funky approximation actually works because it didn't work.
Whatever it takes.
That's fun.
Whatever it takes. Huh.
Yeah. And then it's the points that this approximation is not good for intermediate values of x, but it's very good for when x is approximately 0, is close to 0 or close to infinity.
Right.
Which are limits that we want, because we are integrating this
over
to large size. Exactly. Yeah, we are integrating it over very large sizes.
Yeah,
that's what is showing there on I mean, not show, but if people want to see, that's what is shown on figure 10. And then equation 67 is a result of this approximation. Oh yeah. So on figure 10 there, that's the difference between the integral of the square root of 1 plus x and this approximation 1 plus the square root of x. As you see, it's not really a good approximation for 1, right? It has this bell shape.
Oh, sure.
But if the x max, the maximum integration, is very small, it is a very good approximation. And if it's very large, it's also a very good approximation. Essentially, of this approximation. So equation 67 is is using this approximation to try to solve the integral. You split it out 4 integrals.
Yes. 1, 2, 3, 4.
And if you say and all of these integrals have the shape of equation 68.
In complete gamma.
Yep, they all have the shape here, an exponential times that AB, and then it turns out that this integral has an analytical solution. That's this incomplete low complete gamma function. I literally went to SymPy, right? Symbolic Python, put it there, and then spit out lower incomplete gamma function. I was like, what is a lower incomplete gamma function?
Remind oneself. Very cool.
It is there. So lower incomplete gamma function.
It happens.
So you end up finding.
Anyways.
So end up finding on equation 69 the full solution.
Very cool.
Within this approximation. So all these incomplete gamma functions and all, and then the coefficients. The coefficients that go in there are from equation 70 to equation 83. So these are the coefficients that go for you to plug in on equation 69. I was so happy when I found that this works. When I plotted this, I was like, seriously, all of these coefficients will really work. And then I plotted it. That's when I plotted equation 11 and saw that I could reproduce the numerical accretion rate perfectly. I was so happy with that. I wrote back even to my math teacher in high school. So see what I did here?
All right. Very cool. Very nice. Oh, I'm glad that worked out. That doesn't happen often, but when it does, it's pretty cool.
I wrote my, my family, my friends, so on. You are not going to understand this, but I'm so happy about this. You have to see it.
Very nice. Very cool. Congratulations. Congratulations.
So there is the second sharing, yes. So, yep.
That's a third sharing. Yeah, very cool.
In short, that's it. Yeah, we found, then we can go to the conclusions. We found polydisperse bond accretion is up to 2 orders of magnitude more efficient than the monodisperse case.
Yes.
And that's because the best accreted pebbles in the Bondi are those of friction time that are similar to the Bondi time. It's not going to be the biggest pebbles that are present, because the large pebbles, they may dominate the mass budget, but they have low accretion rates because their drag time is too large. They are almost decoupled in the scales of Bondi accretion. They accrete poorly when the protoplanet mass is low, right? And also then the onset of polydisperse pebble accretion is extended to 2 orders of magnitude lower in mass. So you can have Bondi accretion. You start having Bondi accretion on top of the planetesimals that are formed by streaming instability, right? Yeah, up to about 20, 30 AU. Yes. And
cool.
In all the models, the point 3 there, in all of the models considered, we could avoid also this being too efficient. So it doesn't work at 40 AU in the solar nebula. So the planetesimals that are formed at that distance remain planetesimals, right? They do not grow to protoplanets. So we can also explain the existence of the cold classical Kuiper belt population that are primordial planetesimals that are undisturbed, like since the formation of the solar system.
Right.
Well, yeah, that's so that's the paper.
Summary. I want to thank you so much for walking us through your very lovely article. Very cool. Very cool.
Thanks for
congratulations on the analytical integrals. Very nice. So you mentioned it, or you touched on it a couple of times as we went through, and so I'll just push on a little bit here. So where do you think we go with this topic over the next, let's say, 2 to 5 years? Is there additional theoretical considerations to add into it? There's a very large parameter space to cover on that. Is there some observational work that can be done to try and get a handle on a number of these quantities, or do a comparison with observations? So where do you think we go with this over the next couple of years?
It's an excellent question. Yeah, I think that in all of these cases, I mean, observation, theory, and experiments, even. Right?
Yeah,
this is a field that where laboratory
Mm-hmm.
experiments are needed too. Observation-wise, observation-wise, we have 2 main avenues, right? I mean, the solar system and the protoplanetary disks that are being now observed with ALMA. Right? ALMA has been a game changer. Yeah, so we are getting to resolve smaller and smaller detail, but we're not going to get anywhere near yet the scales where planetesimals form, right? The scales of streaming instability. But there are ways that we can bypass that and then try to find out if streaming instability is really happening in this protoplanetary distance or not.
That would be good. Yeah, confirmation of that would be cool.
Yeah. So if the observers, they keep pushing the resolution down and down, that would be great. But yeah, we also needed to find out ways to find the signature of unresolved streaming instability in the observations that we have. And a shout out also to New Mexico, because even though ALMA is great, the next generation VLA is going to be even better, right? For the
there you go,
resolution.
Very cool.
And on the theory side, we should apply this theory and see if there are holes in it. If we try to apply that to the formation of the solar system, does it match what we see? Does it not match what we see? As a theoretician, I would be happy if my theory is fine, but I also want to know if I went wrong, right? So I would like people to go and then try to poke holes in it.
Poke holes in it. Yep.
Yeah, and if that is wrong, then I would like to know why. Now, one of the things also that observations of the solar system would be quite interesting to see is, again, going back to the population of Kuiper belt objects, those cold classicals, right? So they are saying that that is very difficult to explain the cold classical population as being formed by streaming instability, even though Arakoth seems to have been formed by is completely consistent, right? with our ideas about, kilometer-sized objects being formed in a cold way, not in a hot way, right, by pebbles,
Yes.
and not undergoing significant pebble accretion. When you look at how many Kuiper belt objects are there, how many cold classical Kuiper belt objects are there, the number density of these objects is too low. It's incompatible with having streaming instability have gone and formed planetesimals all over the place there. The number density of cold classicals would be much higher.
Okay.
So that's a problem that we need to solve.
Okay.
And on the experimental size, if we're passing to a distribution of pebbles to form these objects very far out, we have to consider that these pebbles, they're not made of dust, they're made of ice.
Yeah.
Right. And most of the coagulation experiments were done for dust. We need to do coagulation experiments for ice at very low temperatures. We're talking about 20 Kelvin. So we need like a cryo lab to try to coagulate ice, right? So I would love to see that experiment being done.
We'll cross our fingers. But this will be really exciting to see this develop over the next couple of years. Both people looking at the theory and ALMA and some experiment on ice bangs. It'll be really cool. So it'll be really nice to see this develop. So Vlad, thank you so much once again for walking us through your very lovely article.
Thank you.
And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.